and welcome back to the final video, part 6 of the 6-part series, looking at the feasibility of rainwater harvesting in arid environments. For this video, I am going to be doing a run-through example based out of Peach Springs, Arizona on the Wallapai Reservation. Hopefully, the other videos gave you some concrete information on how to determine the feasibility of rainwater harvesting in your area. And hopefully this can kind of just sum up some loose ends if there are any in the videos. The final look at that outline. Again, if you want more in-depth information, I suggest you go into part 2, 3, 4, and 5. They're going to be, those videos are going to have the information needed to determine the feasibility for the implementation of a rainwater harvesting system. So check those out if you haven't already. So just a bit of background, I believe I touched on in the introduction video, but for my graduate research, I was asked to do a feasibility study to determine the possibility of rainwater harvesting in Peach Springs, Arizona on the Wallapai Reservation by their FERTEP agent, or Federally Recognized Extension Tribal Program agent, because there was the construction of a new building, and northwestern Arizona gets a lot of monsoonal rains, and they wanted to understand if it was feasible to use the collected rainwater to cultivate either a native plant garden or cultivation of crops for food. So Peach Springs, Arizona is located again in northwestern Arizona. The Wallapai Indian Reservation sits on about close to 1 million acre feet, but we will just be focusing in their headquarters, or the town of Peach Springs in the southern part of the reservation. Peach Springs sits at about 4,780 feet. The town has an area of 8 square miles with a population of 1,500 tribal members, and it has a climate described as mild and arid. So I collected the rainfall depths for Peach Springs, Arizona from the Prism Climate Group website. The reason for this is because there was not a complete record of rainfall that I came across. There were some rain gauges that were installed in the 70s up until the early 2000s, but since the 2000s, which has had a major impact on the climate in the Southwest, the best was to use the Prism Climate Group because it has more of a complete data set for both temperature and precipitation. If you want more information on how Prism determines or how they calculate their data, I suggest for you to watch video 2 and also read up on the Prism Climate Group resources on their website. So for my research, I used a different time frame. I encompassed the 1980s and did a bigger time frame, but looking back, I realized that 30 years is plenty, especially given that this is how they determine the climate average. So the long-term average was determined to be 9 inches. And again, we used the Indian Meteorological Agency's classifications to determine that anything that is 20% less than the long-term average is considered a dry year. Anything more than 20% of the long-term average is considered a wet year, and then anything in between is the normal precipitation year. And with that, from 1992 to 2022, there were 8 dry years based off of our classification, 16 normal years, and 7 wet years. And this kind of makes sense because, as I mentioned there, the Southwest is currently in one of the longest droughts, so the dry years are slightly higher than the wet years, and your normal years should it's mostly the average, so you should see a higher number for that. If you want to learn more about classifying this climate record into a dry, normal, and wet year, that is available in video 2 as well. So listing the averages per month for each average dry, normal, and wet year. We have the information here. The average total for a dry year, so this is including all months, is going to be 5.72. For a normal year, we should see that average of about 9 inches. And for a wet year, we're going to see something closer to 12.6 inches. And however, for my research, I solely focused on the growing season for the area. And the reason for that was because the client wanted just to know how much they can use for irrigating crops. And because it does get really cold and water freezes in Peach Springs, Arizona, there is a lot more that needs to go into the cost and maintenance. And so with this, the cost decreases if you're just doing it for a certain amount of time frame. And but you're more than welcome to encompass the entire year if that's something that you desire. So for the rainwater harvesting equation, it is going to calculate the volume of rainwater that can be collected based off the rainfall depth of your desired period, as well as the multiplied by the area of your catchment, in this case, the roof, multiplied then by the runoff coefficient, which is the material of the catchment. In this case, here's a photo of the 4-H building that's being considered for rainwater harvesting in Peach Springs, Arizona. It has a roof size of 2,290 square feet, and it is composed of galvanized metal, giving us a runoff coefficient of 90% or 0.90. And again, just to reiterate, that is just based off of the material of the roof. And in video 2, you can get the runoff coefficient for various materials. In this photo, this is the area that is being considered for the garden, either for native plants or for growing crops. So when calculating the volume that can be harvested, so during a normal precipitation year, our rainwater harvesting equation determined that based off 0.378 feet or about 4.56 inches of rainfall, multiplied by the rooftop of 2,290 square feet times the runoff coefficient of 0.90, a whopping 5,857 gallons can be collected just during that short time period of April to September for Peach Springs, Arizona, which is really exciting. That is quite a lot of water if you think about it. So for a dry year, we should expect to see less, which is the case with about 0.256 feet or a little bit over 3 inches. We get a total of 3,957 gallons that can be collected. And just so you know, the only thing I'm changing from this equation between my normal dry and wet precipitation years is the rainfall depth. The area is going to stay the same, as well as the runoff coefficient. Those aren't changing. So still quite a bit, even though a dry year we get less, like about 3 inches in this area. Now for a wet year, we get a total of about 0.373 feet or about 4.46 or 48 inches, giving us a total of 5,752 gallons that can be collected during a wet year during the months of April to September, which is kind of interesting because if you look at what we could collect during the normal precipitation year, which we'll look at, we get a total of 0.378 or about 4.56 inches, while a wet year you get 0.373 or about 4.48 inches. And that's what I mentioned in video 4 about it being interesting with the data. If we look at the growing season for both the the normal year and the wet year, our totals are about 4.56 averaged, and then for our wet year, we get 4.48. And you would expect to have more rain during a wet year, correct? But if you look, you can see that our December's months and our January months are actually a lot higher. So it looks to be that whenever there is a wet year, most of that additional rainfall is coming in during the winter month, which is very interesting. There's probably some explanation for this that I haven't determined yet, but I thought it was pretty interesting and something worth sharing with on these videos. So moving on, we calculated the net irrigation using the aquacrop model. And the net irrigation is just the required amount of water a crop needs to yield healthy harvestable crops at the end of the growing season. And we did this for maize. Again, the aquacrop model has various default crops, or you can input information about the crop you desire. The net irrigation simulated the amount required for each a dry year, wet year, and normal year, which showed that during a dry year, about 1.1 feet of water is needed in order to sustain a healthy crop. A normal year would need 1.06 feet, and a wet year would need 1.04 feet of irrigation, and that's per crop. So to go back on how we saw that the wet year gets less precipitation during the growing season than a normal year, the reason why less water is needed for irrigation is that we need to consider the temperature. During a wet year, you have cooler temperatures, and that's something you can determine looking at the temperature data that was also collected using the PRISM Climate Group data sets. Because there's cooler temperatures, you require less irrigation because there are lower evapotranspiration from the crop. So meaning that although you receive less water during, at least for Peach Springs, Arizona, there's less water during the wet year, your crop will still require less irrigation because of those cooler temperatures. So the next part would be the area that can be cultivated. And this is the area that can be cultivated for the desired crop. And we're going to determine that by dividing the volume of the captured rainwater by the net irrigation simulated in the aquacrop model. And this is going to give you an answer for how much that volume of water based off the net irrigation can cultivate a specific area. So for a normal year, based off the volumes that we determined from the rainwater harvesting equation and the simulated net irrigation from the aquacrop model, we get an area that can be cultivated of approximately 741 square feet. For a wet year, we have an area of 742 square feet. And for a dry year is a lot less, which is 479 square feet. So now that we have that information, we would like to know what the dry yield is going to be for our crop. And the dry yield of maize was also simulated in the aquacrop model. And that's going to be, if you want more information on that, that'll be in part 3. It is calculated as ton over hectare. I like to convert it to something that's a little bit more familiar, so pounds over square feet. And this is going to give you the actual yield when you multiply it by the area that is being cultivated. Here we have the aquacrop model simulated that about approximately 14.2 tons per hectare of corn can be cultivated if you use, or the simulated net irrigation, which I believe we said was 1.06 for a normal precipitation year. And with that information, we determined the area that can be cultivated. So just from some simple unit conversion, we can collect approximately 196 pounds of maize if an area of 741 square feet is cultivated solely using the harvested rainwater. And so for a normal year, we can expect about 196 pounds of maize. A dry year, we're going to see less, so 126 pounds of maize. And then for a wet year, we should kind of see similar numbers to the normal year because of our fun little discovery. Remember, this is only for the growing season. and only for this specific crop, and it is only using the harvested rainwater. Of course, you can always increase your yield if you decide to add or contribute to your irrigation system. So for the cost of maintenance for a rainwater harvesting system in Peach Springs, Arizona, the main thing that is going to be the most costly, it's going to be the cisterns. And it's going to require a capacity of at least 5,857 gallons. And that's to optimize the rainwater that can be harvested during a normal precipitation year, which I would suggest over getting something that would only collect enough water for a dry season or something that could collect water for a wet season. In our case, because the wet and the normal are pretty similar, going with just enough capacity for the normal year, precipitation year, should be more than enough. Again, that is the capacity that can be collected from a single building. Rainwater harvesting system would require a drip line and a hydraulic pump or a elevated platform to get that grade for gravity-fed irrigation, and of course, piping. Because this is going to be used for outdoor irrigation, it is going to require a very low and simple maintenance. In our cost and maintenance video in part 5, we talked about the various maintenance required to maintain a rainwater harvesting system and to keep it going. So there's more information in that video if you would like more information on that, as well as different resources of where you can get additional information and or purchase this material. So to conclude the rainwater harvesting video series, rainwater harvesting can help alleviate some of the stresses associated with water security for food production. In Peach Springs, Arizona, there is quite a distance before you get to the first grocery store. So if you think about attaining food sovereignty in environments that are arid, collecting rainwater can help with those stresses. Simple information can help calculate the average rainwater that can be collected and also determine the area that can be cultivated and what the yield of your crop would be at the end of the growing season. Although it probably won't replace your current irrigation methods, it can help alleviate that if there are some stresses or add additional water to cultivate a larger area. The great thing about the rainwater harvesting is that it's scalable to any environment, even with arid and semi-arid climates. Quickly, an average 3,850 gallons of rainwater can be harvested with only 3 inches of rain on a 2,290 square foot roof. And for this entire series, we just looked at the feasibility of harvesting rainwater during the growing season. You can also harvest rain during the winter season, but as I've mentioned before, that would require a little bit more engineering, might increase the cost a bit, but if the benefits outpace the cost, then it is well worth the investment. So I would like to thank you all for watching the 6 videos, and if you have any questions about this project, please feel free to contact me at briandahernandez90@outlook.com. and or Dr. Maureen McCarthy and or Dr. Lutz at their respective emails. Again, this project would not have been done without the support from Native Waters on Arid Lands, as well as the Wallapai tribe and the FERTEP agent for the tribe. So again, thank you for watching. Hopefully this was helpful and you have an idea of how to determine the feasibility of a rainwater harvesting system for your area. Thanks.